All right, so we're going to finish up section 5.4, which is part 2 of kind of introduction to vectors. All right, so first thing I'm going to do, really simple idea, is just what it means for two vectors to be equal. Okay, very simple way to say two vectors are equal is that their components are equal. That's it. Okay, two vectors are equal as long as their components are equal. Okay, it doesn't mean that when we sketch them, they have to be sketched in exactly the same spot on a graph paper. So, for example, say I wanted to sketch the vector 2, 3. I could put it here, or I could put it over here. Even though those two vectors are in different spots, they are equal. Okay? As long as if you were to move them to the same spot, they would be exactly on top of each other. Okay? So same horizontal components, x1 and x2 equal, and same vertical components, y1 and y2 are equal. Okay, so any questions on what it means for two vectors to be equal? Okay, it doesn't matter where you sketch it. All right, so if I ask you on a test like a true-false question, do two vectors have to be drawn in the same spot to be equal? The answer is no. Right? Their components have to match. That's it. All right, so we've done vectors visually. Okay, I just gave you guys an example of that. We've done this other notation where we use these angled brackets. And now we're going to look at the last way we can write a vector. And this will be the way we use most often now. Okay, called unit vector notation. Okay, so first thing we're going to do is look at two special unit vectors. Somebody remind me, what does that mean if a vector is a unit vector? It equals 1. Its length is 1 unit long. Okay, so we're going to look at two vectors here that both have a length of 1 unit. Okay, the first one I'm going to look at is vector I, and that's a unit vector that points 1 unit to the right, and vector j, which is a vector that points 1 unit up. And basically, what we're going to do is we're going to stack these i's and j's together. Okay? And by stacking them together, we can kind of build any vector that we want. Okay, and I'll show you an example. Okay, so what I've drawn over here is both of those vectors I just mentioned. Okay, I points 1 unit to the right, and j is 1 unit up. Okay, does everybody have what's on the left? Okay. So we're going to kind of think of these two vectors as building blocks. Okay, we're going to stack them together just like we did yesterday. And the first time I do it, I'll do it visually just to show you, okay, kind of what this looks like. But after that, we're just going to do it in our heads. Okay, we're not actually going to be graphing every time. I'll give people a second to copy what's on the left. Anyone still copying what's on the left? All right, so what I'm going to do on the next page is I'm going to build the vector 3, 4, okay, out of these two. Good? All right, I just want to make this page, it's kind of small to see these, so if I make it a little bigger, you'll see it better. All right, so what I did is I just made a copy of an I vector, okay, that points 1 unit right, and a copy of a j vector. that points 1 unit up. And I'm going to use those as my building blocks to make the vector 3, 4. All right, so first thing I look at is the 3. Is that my horizontal or my vertical? That's my horizontal. You know what I'm going to do? I'm going to make these a different color so they stand out a little bit. All right, so I'm going to put 3 eyes together. Okay, the reason I need 3 of them is because my horizontal component is a 3. Okay, so I'm going to stack 3 eyes together. There's 1, there's 2, and my third one. Come on. There we go. Hey, any question on that part? So what I just did is I built the vector 3i. Questions on why this vector right here is 3i? It's just 3 i's connected, so that's 3i. Okay, plus, okay, now I'm going to build the vertical component. How many vertical components do I need?
4.
Yeah, I need 4. So I'm just going to take 4 of these. Let's just make them right now. And now stack all 4 of those together. So we got 1, 2, 3, and 4. Okay, so now I just built the part for J. Okay, now if I connect it, just like we always do from the start to the end, that vector in black is 3i plus 4j. And that's how we're going to write our vectors. Okay, it's almost like what we did before, but you don't need the angle brackets, you don't need the comma, you just write a certain number of i's plus a certain number of j's. Right, now that works fine if we want to be in quadrant 1, but what would we have to do to these vectors if we wanted to get in quadrants 2, 3, or 4? Yeah, make them negative. So for example, if you did 3i minus 2j, that could bring you down. Okay? Or if you did negative 2i plus j, okay, you can get any combination of i's and j's. We can go anywhere we want in this quadrant. Okay? Or, I mean, on all the quadrants. Now, would that work for, let's say you got rid of j's. I only let you use I. Could you get anywhere you want just using i's? No, what does I only allow you to do? It only lets you move left and right. Okay, so if you took away j, all you could do is move left and right on the x-axis. Right? So you need i's and you need j's to get anywhere you want on this plane. Now, could you do 3D, you think, with just I and J? No. All I and J let you do is move flat on this board. If you wanted to do 3D, you'd have to have another letter, another vector, that allows you to come off the board. Okay, so however many unit vectors you use, that's how many dimensions you can work in. We're using 2 vectors, we're doing 2D. If we were doing 3 vectors, that would be 3D. Okay? We're gonna stick with 2D for now. Right, so how about, what if I have the vector negative 2, 7? How would I write that using i's and j's?
Negative 2i plus 7j.
Yeah, that's it. Negative 2i plus 7j. Okay, how about 5, 0?
5i.
That's it. Just 5i. You could put plus 0j, but you don't need to because there are no j's in this one. Just 5i.
If it was negative 2, negative 7, would it be negative 2i minus 7j?
Yep, that one would be negative 2i minus 7j. Okay, so it's not really a big step to go from writing it this way to using i's and j's. Just think of it as stacking little vectors together, just like we did there. Okay. All right. Next thing we're going to look at is some formulas for vectors. Okay, some of these formulas we've already done visually, like I showed you how to add vectors by drawing pictures. Now I'm going to show you how to add them just with numbers. Okay, in all these formulas, I'm going to write v and w are vectors, and alpha is a scalar. So you could remember, a scalar is just a number. Okay, so my first vector, it's going to have components x1 and y1. My second vector has components x2, y2. Okay, so to avoid kind of being confusing, I think I'm just going to stick with one notation. Okay, we'll practice when we do some problems with I and J. Okay, but for now, I think to write out the formulas, it's easiest to do it the way we learned yesterday. All right, if you want to add two vectors together, okay, instead of doing all that stuff where you draw it on paper and then connect the arrows and draw in the diagonal, to add two vectors very easily, just add the x components, add the y components. All right, so now we're going to be able to add vectors without doing any graphing at all. All right, we'll do an example of each one of these. Okay, to subtract two vectors, just subtract their components. x1 minus x2, y1 minus y2. Okay, alpha is a scalar, so you could think of it as like the number 3. Okay, when you put a number in front of a vector, it can make it longer, it can make it shorter, or if it's a negative, it flips the direction. Well, it's almost like a distributive property. If you were going to scale a vector, you just multiply each component by whatever you're scaling it by. So x1 gets multiplied by that number, and y1 gets multiplied by that number. Okay, and the last thing we're going to look at is how we find the magnitude. Okay, how we get the length of a vector. Let's suppose we had, let's make up an example. Okay, there's our vector. And what I'm going to do is make a triangle out of it. Now let's say this was the vector 4, 3. What that would mean is I have 4 units right, 3 units up. If I wanted the length of this vector, how do you think I could find it? Yeah, use the Pythagorean theorem. Okay, finding the length of a vector is just like finding the hypotenuse of a triangle. Okay. If you use the Pythagorean theorem, you would get 5 there. Okay, it just comes out nice. But that's your Pythagorean theorem. Take your x component, square it. Take your y component, square it. Add the two together, just like the Pythagorean theorem, and then take the square root. Yeah, I'm not using a, b's, and c's, which is what you normally use with Pythagorean theorem, because we're graphing. When we graph, we use x and y. Hey, we'll go through one of each of those. Okay, questions on that? All right, so here's our two vectors. Okay, I've written them both ways. Unit vector notation, and then with the angle brackets. All right, first thing I want to find is v plus w. Okay, so to add these vectors up, just combine the x's and then combine the y's. Jake, could you tell me what I get when I combine my x components?
5i.
Yeah, I'm going to write it that way in a second. Or you know what? If you want to do it that way first, we can do it that way first. Yep, 5i. And what about my j?
Negative 1j.
Yep, negative 1j. Or if I were to write it with the angle brackets, Nathan, can you tell me what it would be this way?
It would be 5
Mm-hmm.
and negative 1.
Negative 1. Okay, either answer is correct. It just depends on what they ask for. Okay. Any questions on how we got 5i minus j or 5 negative 1? Okay. Right, same two vectors. This time we'll subtract them. Dakota, can you tell me what I get when I do v minus w?
Negative I
Yep.
plus 7.
Plus 7j, good. Okay, 2 minus 3 is negative 1i. 3 minus negative 4 becomes 3 plus 4, or 7j. And can you write it that way as well?
Negative 1, 7.
Negative 1, 7. Okay, any questions on subtracting? Okay, so hopefully you find it a lot easier than doing it the way we did yesterday. Okay, yesterday we had to take a vector, we had to flip it, then connect them and all that stuff. Okay, we don't have to do any of that today. Okay, 3v. Andy, what's that 3 going to do to vector v?
It's going to just multiply x and y by 3.
So what's the effect visually? What
Or
happens
distribute it.
if I were to draw them? How would they
Take
compare?
that 3 times longer.
Yeah, this is going to triple the length of v. That's all. So as Andy said, basically you're going to distribute that 3 to each component. Can you tell me what I get when I do that, Andy?
6i,
Mhm.
9j.
6i, 9j. Or you could write it, how would it be the other way?
6 and
6 comma 9. Yep. Right, and the last thing we're going to do is find the length of v. Right, so this one you're basically thinking of these as two sides in a triangle. One side's 2, other side's 3. Just use the Pythagorean theorem. So Charlie, can you tell me how I would set that one up?
You, 2 or 4.
Yeah, 2 squared
2 squared, comma, 3 squared.
plus, right?
Yeah, that's
Plus
plus 3 squared.
3 squared. Right. So take the x component, square it. Take the y component, square it. Add them up. Right, so here we get the square root of 13. If they don't ask for a decimal, don't worry about it. What's the difference between this last answer and every other answer above it? It's not a vector. Okay, when you find the length of something, it's just a number. Every other answer I had above it, vector, vector, vector. Okay. Any questions on that? All right, so just a reminder from yesterday, okay, if you have a vector that's 1 unit long, we call that a unit vector. And what I want to do here is try to come up with a formula for getting a unit vector. Okay? So this formula we're going to come up with, it's basically going to, here's a picture of it. We're not going to change the direction of the vector. All we're going to do is, if we have a vector that's too long, we're going to shorten it so that it's a length of 1. All right. So if I had a vector that was, let's say, 5 units long, okay, what would I have to scale that by to make it 1 unit long? Think, what would you multiply 5 by to make it 1? What is it? Yeah, 1/5. Okay, so if you have a vector that's 5 times too long, if you scale it by 1/5 or divide by 5, same thing, it makes it 1 unit. Okay, what if I had a vector that was 10 units long? What would I scale it by to make it 1 unit? 1/10, or divide it by 10. Okay, so the shortcut to find a new vector that points exactly the same way, but it's only 1 unit long, all you have to do is scale it. That's it. You got to scale it by the right amount to shorten it down to 1 unit. Okay, and the way we scale it, you just have to take the vector and divide by its length. Anytime you do that, it automatically will shorten it to 1 unit. So if you had a vector 8 units long and you divided it by 8, or some of you were saying scale it by 1/8, it's the same thing, it'll shorten it to 1 unit. All right, so to find a unit vector, take the vector you have and divide by its magnitude. If the vector is already 1, you don't have to worry about it. It's already a unit vector. If it's not, then we'll do it. All right, so we're going to take the vector 3, -4. First thing we're going to do is find its length. If it's already 1, then we're done. There's nothing to do. If it's not 1, we're going to scale it and turn it into a unit vector. All right, so let's find the length of v first. Okay, Brandon, can you tell me how I would get the length of v here?
You would do 3 squared plus -4 squared.
Yeah, and this is actually the same as the problem. No, actually, it's a little different. We did 2 and 3 before. This one's 3 and 4. So that gives me 9 plus 20 plus 16, which is 25. So what's the length of this vector? Okay, so the length is 5. So is this a unit vector right now? No. It has a length of 5. It's 5 times too long. So we need to make it 5 times shorter. Okay, so how do I do that?
Divide by 5.
Yeah, okay, you could just take this vector, divide each component by 5, or the way some of you were saying it before, scale it by 1/5. You distribute out the 1/5, it's exactly the same thing. 3/5, -4/5.
So what would be that's our answer.
Yeah,
Put it over.
because you'd have to do this out, and you'd get that.
Same thing.
Yep. So now this is a vector. It points exactly the same way. It was 5 units long. We scaled it down by 1/5, so now it's exactly 1 unit. And that's it. That's how you make a unit vector. So just find the length, divide each component by that length. Okay, any questions on converting a vector to a unit vector? Okay, and the reason we might want to do that if we're dealing with a problem where the direction is the only thing that's important. This preserves direction, but it makes the length shorter, makes the length 1. 1's an easy number to work with. Okay. All right, so the last 2 things we're going to do today are 2 word problems. Okay, the first one is it's a little easier. Okay, it's called a velocity vector. And a velocity vector is used to model 2 things. It's used to model the speed and direction of an object. Right, so did we look at the website yesterday with all the planes on it in here?
Mhm.
Yeah, so you could think of an airplane, you could model it with a velocity vector. Okay. How fast is it going? What direction is it going in? All right, so what we're going to try to do is come up with the formula for a velocity vector. Right, so when you throw, think of like when you throw an object to someone. unless you throw it exactly straight and there was no gravity, that object as you throw it to someone is really traveling in two directions. Right? If I toss something to Andy, like that, what two directions was that traveling in? It was traveling forward, but it was also traveling up. Well, up and then it traveled down once gravity took over.
Yeah, like I'm having anxiety. I feel like we're going back to physics. I didn't do so well there.
This will be okay. Okay, so anytime something's moving, it usually has two directions to it, whether it's traveling forward and up, or if it's traveling forward and down. Usually, unless you just drop something straight, that's the only time it's traveling in one direction. Right, so what I'm going to do is take this vector, I'm going to break it up into a triangle. Okay? So this particular vector has two directions to it. This is one. There's a component that's going right. And there's also a component up. Together, if you put the red and green, you get the vector in block. Okay, and we talked about that visually yesterday. I'm going to call that angle alpha. You could call it alpha, theta. That's what your book uses, so that's what I'm using. Right, and for now, let's call these sides x and y. All right. What I want to do is come up with a formula, okay, using two trig functions that tell me the formula for this red arrow, and then separately a formula for this green arrow. All right.
Oh, are these like cosine, sine, tangent?
Yep. So this vector that I circled at the top, the v, what side is that? It's hypotenuse. And is x adjacent or opposite? Adjacent. So which trig function has hypotenuse and adjacent in it?
Cosine.
Cosine. Okay, so I'm going to write that down. Okay, so I'll just put for, well, you probably don't have color, so I'll just say for bottom vector. Or horizontal, yeah, we could, that'd be even better. All right.
Oh my God, physics.
So-
Here I come.
Cosine is adjacent over hypotenuse. So x divided by, now I don't really care about the direction of v. All I care about is its length. Okay, whatever the length of that vector is, that's the hypotenuse. Okay, that's all I care about. And now my last step, how would I get x by itself?
You multiply by the magnet? No, yeah, maybe multiply by the bottom?
Yeah, multiply by the
I was
magnitude of
doing
v.
so good, yeah.
Okay, whatever v is, just going to move it to the other side. Okay, so there's a formula that models just the horizontal component of whatever this is. Say you're throwing an object. That black line is you're throwing a baseball to someone. Okay, this is the horizontal component. Okay, like when I threw that object to Andy, it was traveling towards him. This is the speed traveling towards him. Okay, but also as I threw it, it was going up and towards him. Okay, now we're going to look at the upward component. Which trig function would I use for up?
Sine.
Yeah, this is opposite. Okay, I'm still using hypotenuse, but now I'm using opposite and hypotenuse. That's sine. Okay. So this is for the vertical vector. This is the one in green. So sine is opposite over hypotenuse. Y over the length of V. And do the same thing. Okay? Multiply each side by magnitude of V, and that gives you a formula for Y. Now, when we take these two boxes, put them together, this models the velocity of our object. The first box with cosine models horizontal. The second box models the vertical. Okay, so there's two ways we can write it. We can write it as angle brackets, or we can write it with I's and J's. Okay, as an angle bracket, it would look like this. Your X is magnitude V cosine alpha, and your Y is magnitude V sine alpha. Or you can just write it with I's and J's. Magnitude V cosine alpha. Whatever number that comes out to, that's the I. Plus magnitude V sine alpha. And whatever number that comes out to, that's the J. Okay, now if you look at it the second way, what do both these things have in common? What do they both have in common? So in front of each trig function, what do you have?
The length of magnitude.
Yeah, you have the length of V. So a lot of times what they'll do is instead of writing it twice, they just put it in front once like this. And you think of it as a distributive property. All right, so this is the first way you could do it. That's the second way. This is I think a little shorter than what's above because you factored out the magnitude V. If you distribute it back, you get exactly what you had up above. Okay, so that's your velocity vector. Okay, there's only two things they have to give you. The speed that you're throwing the object at, and the angle that you're throwing it at. And both of those two things go right into our formula. Magnitude V, that's the speed. Alpha, that's the angle. Right, so that's... I'm going to do it with I's and J's because that's how your book does it. Okay, and now that we figured out what this formula is, we never have to figure that out again. Okay, we're just going to use this formula. They'll tell us each thing, just plug them in, and that's it. All right, so the example says we're throwing an object at 50 miles an hour at an angle of 30 degrees. Okay. Step one, find the velocity vector. Okay, and they ask us to write it in unit vector form. That means I's and J's. Okay, so what's my speed? How fast am I throwing it? 50. That goes right there. 50 times cosine of, now I need alpha. Alpha is the angle I'm throwing it at. 30 degrees. That's going to be the horizontal. Okay. Plus sine, my angle is the same as it was before, 30 degrees. J, and that's my vertical. Okay, now we're going to just round it off. Find the cosine of 30 on your calculator, then multiply by 50. What's that? Yeah. Okay, yeah, we'll just round to 2 decimal places. Okay, what do I have to check on my calculator first? We're going to be in degrees. If I can get to degrees, I'll do it in degrees. Okay, so just make sure you're in degrees first. All right, so I'm going to find 50 times cosine 30. Just type it in just like that. So 43.31. That's I. And now do 50 sine 30. And that's J. Okay, 25.
That's it?
That's it. That's the velocity vector. Oh, just leave it just like that. Right, now, the last part they say they just want us to look at our answer and explain what each part really means. What is that 43.31? Well, my initial speed is 50 miles an hour.
Your horizontal distance.
How far you're going, like right or something.
All right, it does have something to do with horizontal, but it's not a distance. It's my horizontal speed. So in other words, if I throw this object at a 30-degree angle at 50 miles an hour to Andy, or if I just throw it straight at him at 43 miles an hour, it's exactly the same thing. It's going to take the same amount of time to get there. Okay? So this is how fast the object is coming at you. If you were to throw an object at a wall, it's how fast it would hit the wall. What about the 25? That's my vertical speed. Okay, in physics, you've probably learned like the second you release something from your hand, it's slowing down, right? So the vertical speed is 25 miles an hour the second that object leaves my hand. Right after that point, it starts slowing down vertically, and eventually it hits its highest point and comes back down. Okay. Horizontal speed would stay the same. If we ignore air resistance, this speed would be traveling 43 miles per hour the whole problem. But because of gravity, the vertical speed would not. Any questions on that? All right. Okay, so the good news, we're on our last problem. The not so good news, it's a little hard, but we'll work through it and see what we can do.
It's okay, I passed physics, I can do anything.
All right, so for the last problem we're going to look at is called static equilibrium. So static, does anybody know what does that mean if an object is static?
It's not moving.
It's not moving. Okay, so we're talking about something not moving, which makes things a little easier. Nothing is in motion here. That would be harder. And equilibrium means all the forces acting on the object are balanced. Okay, for all the objects on this table, they're all in static equilibrium. The force pushing down on them is gravity. The force pushing up is exerted by the table. That's why my book is not moving. All the forces are balanced. Okay? If something's in the middle of falling, forces aren't balanced because it's in motion. Okay, so we're going to deal with things that are staying still and all the forces are balanced. Okay, that's all you really need for background. Now we're going to try the problem. All right, so the basic idea in this problem is you've got a weight. It's being suspended from a ceiling by two cables. The cables are not the same length. And I want to find how much tension is in each cable. Okay, so where you might use this kind of thing is, let's say, I don't know, you're going to put up a traffic light, right? And it's going to be suspended by cables. It's not going to be on a pole. They might have to find out, depending on the length cable, how much tension is that light going to put on it. And we got to get a cable strong enough that it doesn't break. And of course, maybe you want to make it even stronger, so like if the wind blows and stuff like that, it's just really strong. All right, so here's our setup. 1,200-pound object. If the length of each cable was the same, then the tension would be split equally. If both of the cables were vertical, this would be really easy. It'd be 600 pounds of tension in each cable. Okay. But because the cables are at an angle, they're slightly pulling against each other. Okay? Think, what would happen if I just clipped that cable on the left? This weight would do what?
Swing
It would swing to the right. So what that means is this cable is not only pulling up, because it's holding the weight up, it's also pulling left. Okay? Same thing on the right. If you were to snip that cable on the right, all of a sudden it would swing to the left. So this cable is pulling to the right, and it's also pulling up. Okay, so that's important to understand. So if this object is not moving, what does that mean about the force pulling up and the force pulling down? They're equal. So force up equals force down. And it's not moving left or right. So that means the total force pulling it left equals the force pulling it right. Okay, the only thing we have to do now is figure out all four of these things using the angles that we're given. All right, so what I'm going to do is let's draw some arrows. So I'm going to make triangles out of out of these two vectors. Okay. This vector on the left, okay, it's pulling to the left. Okay, we know it's pulling to the left because if you cut it, all of a sudden that would swing to the right. Okay, so some component of it is pulling left, and it's also pulling up. If it wasn't pulling up, this 1,200 pounds would be falling to the floor. Okay, and exactly the same thing with the cable on the right. Okay. It's pulling to the right, because if I cut it, all of a sudden the weight would swing left. So it's pulling right, and it's pulling up. These are both 90-degree angles. Okay, any questions so far? Now the angles that they've given me, they're really outside my triangle. I want the angles inside. Okay, so starting with this triangle on the left, what would the angle at the top be? 60. And then the angle at the bottom? 30. Okay, and starting now the triangle on the right, what's this angle at the top? 45. That's a 45. And of course, if it's a 45, 90, the other one's 45. Okay, any questions on that? All right, now I need to label. The tension in each cable. So let's just call it tension 1, and that'll be tension 2. Okay, T1 basically represents the length of that vector in black. It's the hypotenuse. Right, now let's see if we can find all four of these things. Okay, how many forces are pulling up in that diagram? Look at everything that has an arrow up. 2. Okay, the green forces are both pulling up. Let's see if we can find what this green force is. And all we're going to need to use is sine and cosine. I'm going to use the 30-degree angle. Okay. What side is that green one? Opposite, adjacent, or hypotenuse? Opposite. And then T1, is that adjacent or hypotenuse? That's hypotenuse. If you want, I can label it over here if that makes more sense as well. Okay, that's the hypotenuse. Which trig function has opposite and hypotenuse? Sine. Okay, so we're going to do this same thing 4 times. Sine of 30 equals opposite over hypotenuse. Now, I got to give some kind of name to this thing in green. What do you think it would be a good name to give it?
U for up.
U for up? All right, so let's call it up 1 and up 2. Okay. So side of 30 equals opposite over hypotenuse. Okay, and my goal is to figure out how to get up by itself. So how would we move T1 to the other side? Multiply. So my first force pulling up is T1 sine 30. That's one of my forces pulling up. Does anyone think they can do the other force pulling up without doing out all this work? It's going to be T2 sine 45. Basically, just change the angle to the one you're using, change the hypotenuse to T2. Okay. And force down, I already know. The force down is the weight. That's 1,200 pounds. That's what's pulling down. Okay, so you don't have to worry about force down. Right, now we need force left and force right. Okay, what would be a good name for left and right? Yeah, what could we call those two vectors in red? Yeah, just call it L and R. How many forces are pulling left? Just one. How many forces right? Just one. Okay, so we just have to find what those two forces are. And we're going to use another trig function, but it's not going to be sine. Sine is the verticals. Which one do you think we're going to use this time?
Cosine.
Cosine. Okay, so I'll set the whole thing up the first time. Cosine is adjacent over hypotenuse. And how do we get T1 on the other side? Multiply. So my force left is T1 cosine 30. Okay, and what about my force right? Let me look at it. T2 cosine 45. Yep. Okay, so I got left, I got right, so I can balance that. I've got up, and I've got down. All right, so as far as the trig part, okay, there's no more trig involved in this. Okay, now it's just figuring out how to balance and set this up. All right, so we got force up equals force down. So force up is U1 and U2. Okay, so we're going to add those together because they're both pulling up. They're working together. Both cables are holding it up. Okay, and what are they holding up? How much weight? They're holding up 1,200 pounds. Okay, so this is force up, force down. Right, and now force left equals force right. So T1 cosine 30. Whatever force is pulling left, that same force has to be pulling right. T2 cosine 45. So this was force left, force right. Right, now if you look at each equation, how many variables are in each equation? look at this, just read this top one. How many different unknowns do you come across? 2. How about in the bottom one? 2. And we have 2 equations. Okay? However many unknowns you have to have that many equations or you can't solve it. Okay? If you didn't have this bottom equation, you'd be stuck. Okay, so how do we solve that? 2 equations, 2 unknowns. Now this is the algebra part. Okay, what if I had something like this? 2x plus y equals 12, and x plus y equals 3. How would you solve that?
You have to make the bottom one match the top. Just don't you add straight to the columns, or am I thinking?
Okay, yep, there is one method you can add or subtract columns. That method won't work here. So what we're going to have to do here is, I'll give you a hint. Start by doing this.
Oh, and then you plug it in for the top.
And you plug it in.
Yeah.
Okay, that's substitution. So you take one equation, you get one of the variables by itself, and you plug it back into the top one. This is not something I taught you. That's like Algebra 1, Algebra 2. Okay, so you have to substitute back in. Okay, it does not matter which variable you get by itself. Whatever one you do, that's the one you're going to solve for first. Okay? All right, so in this bottom equation, you want to get T1 or T2 by itself?
T1.
T1? All right, let's do T1. Okay, how would we move cosine 30 to the other side?
Divide.
Yeah, divide. So, okay, so T1 is T2 cosine 45 divided by cosine 30. That's the formula for the tension in cable 1. And now, what am I going to do with that formula?
Plug it into the. Yeah.
Plug it in. Where are we going to plug it in? Right there. And once I change that box to that box, I'm not going to have T1 in that whole top equation. It's all going to be the same letter. Then we can just solve it with our calculator. Okay, so just write out that top equation again. Change T1 using substitution. Okay, and eventually we have to start getting decimals and do this out. Okay, so there's T1, which I just wrote down, sine 30. Plus T2 sine 45. Equals 1200. Okay, and now the easy part, let's just type all this in and see what we get for decimal. Okay, so we got cosine 45. Okay, make sure you're still in degrees if you changed back to radians. Times sine of 30 divided by cosine 30. Okay, so we get 0.408 T2. Okay, sine of 45. That one I just know it's 0.707. If you want to type it in, go ahead. Okay, and now what can I do with 0.408 T2 plus 0.707 T2? Yeah. Yeah, just combine them. This is like 2x plus 3x equals 7 now. Okay, combine your like terms. Okay, so we got 0.408 plus 0.707. That gives me 1.115. And my last step, how do I get that 1.115 on the other side? Divide. So there's a ton of stuff happening in this problem. I think what makes it hard is there's so many little things from Algebra 1 and Algebra 2 and right triangles you have to remember. But the nice thing is every single problem is like this. There's no tricks, nothing ever changes. It's the same process every time. Okay. All right, so this is the kind of problem where you definitely might have to go back and just watch it again. You're not going to get it first time through. Okay, so 1,200 divided by 1.115. Okay, so that's the tension in cable 2. It's 1,076.2 pounds.
Now, if we're really confident that we got T2 correct, can we just subtract 1,076.23 from 1,200 to get T1?
Are these cables just pulling straight up?
Oh, no.
They're pulling at an angle. So the total tension is actually going to be more than the weight because the cables are pulling against each other, okay? Which usually happens. But T1 is very easy to find. It's right there. T2, cosine 45 over cosine 30. You already have a formula for it. Okay, so T1 is T2, cosine 45 over cosine 30. Type that in, and then we'll have the tension in cable 1. What was the angle on the top? Cosine 45 divided by 30. Okay, so the tension in cable 2, 878.7 pounds. And again, you might be wondering, well, wait, the object only weighs 1,200. It's because the cables are not pulling straight up. They're also pulling against each other. Okay? Think of it as like a tug of war. There's a lot of tension because they're fighting each other. Okay, so definitely not an easy problem. That's a challenging problem.
Where did you just plug this T1?
Oh, how did I get T1?
So you remember how we had to
So the first step in our substitution, that's where I got that from.
Yeah, no, remember how we got T1 equals blah, 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 and then we plugged it in and we went to the top equation? So like we took the second equation, set it equal to T1, and then we plugged
Does anybody have any question on how we got T1?
T1 is already equal to something, so you just was not.
All right, so again, don't get overly discouraged if you were challenged at this problem, because it is a hard problem. It is a difficult problem. It's probably the most difficult problem we do all week today. Okay. So on the homework, I think at most there's one, and that's it. Okay. All right. So what I'll do is, if you have questions, I'll come around and I'll help you out. But I want to give you like 10 minutes to kind of start things and ask me questions if you need to. Okay, so homework, same page as last night. Okay, 344. Okay, 25 to 47, that's just the odds, don't do all. Okay, just odds. And then 55, 57, 66.